All right, thanks, Matt, for the introduction. I'm very excited to be giving this talk. And I just first wanted to talk a little bit about the motivation for this talk. So we just announced that RayTrain is GA yesterday. And over the past year of working on RayTrain and talking to users and customers at any scale, there have been many common questions popping up when people get started using RayTrain and just get started doing distributed deep learning in the first place. And this talk is meant as a way to consolidate the best practices and recommendations that we give people when people are getting started. So this will definitely not be an exhaustive list of everything you need to know about productionizing and distributed training, but it should give you some common questions to ask yourself when you start to scale out your training with RayTrain. Okay, so I'll first give a brief overview of the topics we'll be discussing. First, we will cover the recommended way to set up a Ray cluster. This is more of a prerequisite, so we won't dive too deep into this point. So we'll mostly focus on the next few points. The first one is best practices for configuring resources. So this relates to configuring and optimizing the compute usage, as well as determining the scale of your distributed training. Then we will learn how to use some of RayTrain's features to productionize your training job to make it more observable, as well as resilient to failures. And then lastly, we'll have a demo that shows a fault-tolerant stable diffusion fine-tuning script that's running. We'll do some investigation of observability metrics and take a look at best practices that we can apply in practice. So I also wanted to introduce the high-level overview of the architecture that we're going to be discussing today. So we'll go over these pieces one by one throughout the talk, so don't feel pressured to need to process this entire chart right now. This is just to introduce the components that we'll be talking about. But the general gist is that if you just think about it in terms of the demo, which is going to be this fine-tuning script for stable diffusion, that's kind of the central piece that we're going to be tackling and adding on certain components throughout the talk. Okay, so for the first kind of prerequisite section, we want to figure out what's the recommended way of setting up my Ray cluster. So our recommendation is the best way to run Ray on open source is running with kuberay on a Kubernetes cluster. So we'll start with our Kubernetes cluster, and then we can easily install a kuberay operator on top, which allows us to just write our RayTrain application and not need to think about how these Kubernetes pods are being managed underneath. So kuberay also exposes, in this ecosystem, we also want to set up tools like Grafana and Prometheus, and this will be used later on when we show live streaming of metrics in the Ray dashboard when we're diagnosing bottlenecks and issues with our RayTrain fine-tuning. Kuberay also exposes a Ray job container, a custom resource definition, which allows you to take some end-user fine-tuning request, package that as a Ray job, launch this RayTrain fine-tuning script in its own cluster, and then at the end, when the script has finished, we'll actually clean up this Kubernetes resources underneath. So there have been many talks on kuberay with examples of usage in production at Ray Summit, so I'll refer you to those for more information on this. Okay, so now moving into the first main topic, which is best practices for configuring resources. So we have our Ray cluster set up. A common first question is figuring out the resource requirements for our worker nodes, as well as how much horizontal scaling I should actually do. So how to actually utilize distributed data parallel training. So to start off, I just want to give some factors that you want to consider, and we'll be touching on these throughout the talk, which are these factors to consider when scaling training. So I care about the training speed. So for example, if my model or data size is very large, if I'm just doing single device training, it's going to be prohibitively slow, and we'll need to distribute in some way to multiple devices and multiple nodes even to actually make this feasible to train. And another kind of factor that you might want to consider is if you want to optimize for training speed in order for your model to reach a certain level of test performance within some time budget. So for example, if I'm building some fine-tuning service where I need to give a customer a fine-tuned model by a certain time frame, like this latency might actually matter a lot. Another axis is the cost. So I want my training to stay within some dollar budget. And then with these two in mind, I don't want to necessarily sacrifice model quality when I'm trying to optimize for the speed. Okay, So now, given these considerations, it's a natural question is to kind of ask, how do I speed up my training by doing distributed training with rate train while keeping the cost in check? And so just coming back to this reference architecture, we'll first focus on how to specify the resource requirements and the scaling of our distributed training. These are two kind of knobs that you can turn in your application that will kind of affect this, the training speed as well as the cost. So the scaling config API in rate train allows you to configure both of these knobs. And this is like often, these questions are often one of the first few that we get asked when we're helping users. Okay, so I'll start off by giving some rules of thumb for configuring your compute. So this is like the first question in green over here. So the first topic here that people naturally go to is, how do I pick a GPU? And so different GPUs have different capabilities. And so they have different levels of performance. And so I might want to pick a better performing GPU that will decrease the time for my training, but it will also be more expensive per GPU hour. There's different GPUs have different support for mixed precision training. And so this will be more important when you want to utilize mixed precision training in large language model training. And the main bottleneck that people run into these days is different amounts of GRAM. So on the GPU, you'll have many of these components allocated on the GPU. And so you'll have the model parameters, gradients, optimizer states, as well as the data batch, and the activations that are computed on the data batch. And so ideally, you want to pick a GPU where your training, your full model training state, and so those are all those components there, fit into GPU memory. And this is so that we don't have to introduce extra overhead or extra tricks in order to kind of sacrifice extra compute for memory. If this is not possible, for example, if your model just doesn't fit, like if your model parameters themselves don't fit in memory, and you can't even fit any of these other things, then you'll have to switch to some other strategies. So I'll just briefly cover some of these tricks that people do in practice. This is just a small list of common techniques that you'll see. But in general, we'll want to avoid these tricks because they mostly trade off memory for extra computations that need to be done. Okay, so if your model state doesn't fit into GPU memory, you might want to try one of these. So mixed precision training, as I mentioned earlier, state sharding, so this is going to be the model, gradient, and optimizer states. CPU offloading of the optimizer and gradient states, as well as activation, or it's also called the gradient checkpointing. So all of these will kind of decrease or offload some of these blocks that I have listed below, either onto CPU memory or just like decrease the amount of memory that each block takes. So again, like we want to avoid these if possible, but these may still be worth doing if the cost savings of training on these cheap commodity GPUs outweighs the extra training overhead that these will incur. Okay, so in addition to GPU memory requirements, training large models often imposes CPU memory requirements. So this is just a few more rules of thumb for CPU memory. So the first thing is to ask, like, what is my model size? So usually when you're doing like some kind of like sharding strategy, at least one node, like one rule of thumb is at least one node should be able to fit the full model parameters into CPU memory. So this is often the case when you do model initialization. You will load it first on like the rank 0 worker, and then you'll shard it to other workers. Another note here is that different checkpointing strategies will also have different CPU memory requirements. If you, for example, gather your entire checkpoint onto the rank 0 worker, then you'll also have to incur another copy of the model parameters. Another knob that you can turn is CPU offloading, and this will also incur more CPU memory requirements. And if you need to load any in-memory data sets, this will also increase the requirements. And if you're using RAID data, and if you've attended the talk yesterday, and you are caching preprocessed data sets, like at intermediate layers, this will also kind of bound your CPU memory requirement. Okay, so moving on, the next thing that we want to talk about is actually picking my instance types. So to minimize the communication overhead, we want to prefer instances with multiple GPUs rather than have a distributed cluster with multiple single GPU instances. And so in this case, I'm just showing this diagram where every single GPU is on a different worker node. and we're doing some kind of like all reduce operation. And we see that there's going to be some latency between each of these edges. And we can minimize that by just kind of consolidating them onto a single node. Note that this is not a rule at all. Like, this is just kind of if we want to reduce communication overhead. We may still want to choose single GPU instances for cost or availability reasons. So this is like not a rule exact rule to follow. Okay, so now that we've configured like what kind of hardware we're using, we'll dive into how to configure the batch size, which is one of these parameters that kind of is affected by data parallel training, and kind of basically configures like how much parallelism you can actually apply to your training. So one rule of thumb is to use the largest batch size possible for your given hardware. So this is kind of like basically you have these two blocks in blue, which will scale with your batch size. And you want to pick your batch size B so that all of these blocks kind of fit almost like just right in GPU memory, so you can get the maximum utilization. So if we want to actually increase our batch size, so this is like the slide I just showed is how to optimize your GPU utilization for a single device. When I start to introduce data parallelism, I can actually increase the effective batch size. And this is like I just want to show like how that looks. So for just a single device, if I'm iterating through with a batch size of B, it'll look something like this, where I'm just iterating through my data set B at a time. And if I increase the number of workers, I can increase the effective batch size. This allows for more data parallelism and increases my throughput by around the number of workers that I'm scaling to. This is like ignoring some communication overhead. So this, the new diagram or the new flowchart animation here is just showing that we have the 4x throughput. And with large models, you often cannot fit a batch size of more than 1 onto your GPU. And so a common trick here is that people will use gradient accumulation to get around this. So they'll kind of simulate a larger batch size by just delaying this backward step. And this is actually a perfect opportunity to scale out instead. So rather than doing this trick, where it's just incurring this like time penalty, like a speed of training penalty, we would rather just scale out and actually use just increase the effective batch size by having more workers and more worker nodes. Okay, so one more kind of advanced topic that we'll talk about is finding the optimal level of data parallelism, or the optimal number of batch size, optimal number of workers that you want to configure. And this is a common question that people start to face when they have a Ray cluster. Because I can technically scale to any arbitrary number of GPUs, so does it make sense to just keep increasing the batch size indefinitely? So the answer is no, we cannot keep scaling out training horizontally forever. The throughput of the system will continue to increase, but the speed up in the actual thing that we care about, which is time to desired performance, in this case, the y-axis is labeled in steps to a desired evaluation metric, eventually tapers off. So this paper from 2018 shows that for over a wide variety of data sets, model types, and training algorithms, that you'll see this general trend where you have first a linear speedup region, then you have some diminishing returns where increasing the batch size no longer results in your training time decreasing. And then you have some period of maximum data parallelism. And for practitioners, we might want to pick this point as the fastest time to convergence that doesn't start to increase the total cost of this training. Okay, so practically, what does this look like? We can start with a batch size that works well before you start scaling out. Then we'll just keep scaling out the batch size and possibly the learning rate along with that. This is kind of based on a linear scaling learning rate heuristic, where if you increase your batch size, you want to increase the learning rate because you have a better estimate of the gradient, so you can take a larger step. This is also not a general rule, so this is just something that you can start out with. Then you want to set the number of GPU workers to meet this target batch size, remembering to max out the utilization for each device. Then you can, if you want to be more metrics driven, you can measure the time to convergence, and then you can repeat to the B through D until your training starts to cost more, or you're no longer seeing this linear speed up in training time. Okay, so now that we've covered these kind of tricks to optimize your cluster setup and your distributed training setup, we're going to move on to how to add a few knobs, add a few features of rate train to actually productionize your training job, to make it more resilient to failures and more observable. So the first thing we're going to talk about actually is best practices for model storage. So in this case, we're just going to jump back to the reference architecture. The first thing we're going to do is set up cloud storage. And we're going to set up our, and then afterwards, we're going to enable checkpointing so that it will automatically get uploaded to this cloud storage. And then we will set up experiment tracking so that these checkpoints are also tracked in a model registry, for example, like 1DB. So the first thing is to set up some external storage. And it's pretty easy in RayTrain's API. All you have to do, I'm not sure if you can see it very clearly, but it's just setting this one storage path config, which is in this case an S3 bucket URI. So in this diagram on the right, I'm just showing under the hood like what's happening when you're reporting checkpoints with RayTrain's API. You report checkpoints, and then if you have this storage path set, it's going to get automatically uploaded to this URI. So that's kind of leading into the next point, which is actually reporting these checkpoints to RayTrain. RayTrain only exposes a very lightweight API to report checkpoints. You basically just report a local directory that you've saved, so you can pretty much just use whatever framework checkpointing tools that you've used before and you're familiar with, and you just report it to RayTrain with this local directory, and it'll automatically get uploaded to the storage path. And then lastly, how do we actually track the best checkpoints in the model registry? After we've called raytrain.report, which is the API to upload the checkpoint and report it, we'll actually just add a little bit more logic, which gets the latest checkpoint and the S3 URI that it points to, and I'll just track it as a reference in 1DB. And so we'll show all of this later in the demo, so no need to pay too close attention to the details here. Okay, one other topic is how to make my training job more resilient to failures. And so this involves enabling fault tolerance. So back to the reference architecture, we're going to be adding on fault tolerance to our script. And so this will leverage the cloud storage and checkpointing that we implemented in the previous step. So RayTrain's fault tolerance works like this. We basically have imagine this scenario where we're training with 4 distributed training workers. One of them goes down. You might be trying to access the cost savings of spot instances where this 4th GPU node gets preempted. In this case, Ray will realize that you're no longer meeting the minimum requirements of the resources that RayTrain is requesting. So it's going to try to auto-scale a new GPU node. So this new GPU node is going to get brought up, and then your training script is going to get relaunched on this new set of 4 distributed training workers. So this requires a few, in order for this kind of flowchart to happen in practice, it requires a few configs. So the first one is to enable a worker level fault tolerance using this failure config. So this max failures equals 3 basically just tells you how many times do I want to retry in the event of training or node failures. The second is what happens after the node gets brought back up, and then you start resuming training. You relaunch the training job on the new set of 4 workers. So in this case, we want to add restoration logic to the top of our training script, and we provide a pretty lightweight API to do this. So we take ray.train.getCheckpoint, which gives you the latest checkpoint, and in the case of kind of a restored experiment, this will be populated automatically by RayTrain. We check if this checkpoint exists, and then we just use this as directory API to download the checkpoint locally and view it as just a directory. And then we can use, again, any of our familiar integrations and checkpointing logic that we already know to load this back. Okay, and then one last topic for fault tolerance is enabling the cluster level fault tolerance. So what this means is, let's say my head node or my cluster completely dies. My cluster goes down, and I have a job retry. I have a job that submits and it gets retried on this failure. Then this job retry will spin up a new cluster that will resume training. And I want to basically configure this thing to happen, to resume from where I left off. So for this, we basically just add a little bit more logic in the entry point of our RayTrain application, which just checks, does a previous experiment exist? If so, I'm going to restore from it. Otherwise, I'll start a new one. So it's pretty simple logic here. And so notice that we're also specifying the storage path as an S3 bucket. So we're just using that as the source of truth. Okay, the last topic before we dive into the demo is how to actually diagnose memory or performance issues. And so for this, we touched on the Ray dashboard a little bit earlier, but this is where we're actually going to go through an example of how would I use this to actually detect a bottleneck in my system. And we're also going to take a look at it during the demo. Okay, so this is so the Ray dashboard provides like many of these tools out of the box. One very important one that's used like very, very often is this Ray metrics dashboard, which shows like a live feed of kind of the history of your GPU utilization as well as network bandwidth, things like that. So one example of situation is this plot that we see, where we have very spiky GPU utilization. So this is, I guess, like the first thing is that we're actually alerted of these issues. Like we can monitor this distributed training job in the first place. That's like one thing that the Ray dashboard enables. And then the second is that this will provide as like a starting point for collecting evidence on like what's actually going wrong in this training. So it turns out after some debugging that this spiky utilization is caused by a bottleneck in the dataset preprocessing that's happening on the CPU. And so the dataset is not preprocessing things fast enough for it to catch up with the GPU computations, which are kind of outpacing the dataset preprocessing computations. So in this case, once we fix the issue, we can actually take a look at the after picture within the Ray dashboard as well, and we can see that we have consistent GPU utilization. All right, so this is just like one debugging scenario that I just wanted to highlight, and this is like kind of a realistic one that we pulled from one of the users that we were working with. Okay, so now I just want to give a demo of kind of all of these components that we were talking about before. And I mostly want to highlight the kind of the APIs that we add into the Ray Train APIs that we use to enable this kind of fault tolerance as well as checkpointing logic, and show this actually in action. So let me just play this video, and I'll just talk over what's happening. So the first thing is just to introduce like what's happening in this script. This is an accelerate script that's just taken like from Hugging Face's tutorial, and all I've done is stripped out most of these like kind of the logic of this application into helper functions that are above. And what's left is just the bare bones of like what the script is trying to convey, like the main training loop. And so in the training loop, we actually return like the metrics as well as a saved checkpoint. So the original script already implemented checkpointing with accelerate's save state API. So we're just reusing that, and we're going to use that later when we code up how to report it to Ray Train. At the bottom here, we actually see the torch trainer definition. So all we have right now is the very bare bones torch trainer configuration, and we're going to be adding a little bit more throughout the demo. But basically, at this point, we're able to launch this training loop across many workers and across our entire Ray cluster. Okay, so the next thing I just want to show is like what we're actually running. It's just also copy-pasted from the Hugging Face tutorial. We didn't really have to change anything here. And this is like the main thing I wanted to show here is like it's pretty easy to just take a script that works already from like some tutorial and then just report it to Ray Train. Now you can leverage a Ray cluster. So these configs are just like all taken from the tutorial. And notice that the model that we're training is this stable diffusion model. So the exact task here doesn't really matter for demonstration purposes, but I just wanted to show that we can scale to like larger models very easily with Ray Train. Yeah, so let me continue this demo. So the first thing that we're going to be doing is configuring the storage path. So that's like the S3 bucket URI that we're connected to, as well as the failure config, which determines how many retries we'll try when a node goes down or when we have a training failure. So let me speed up a little bit. Okay, so we're basically just defining the run config. And here we pass in the storage path, which is just a predefined S3 URI, and also the failure config as before. Okay, next, we want to set up checkpointing. So as we saw before, we're just taking this like already existing checkpoint directory that's being dumped every some number of steps by accelerate, this original accelerate script. And we're going to report it to Ray Train using the Ray Train report API. So notice it's as simple as just like passing the metrics corresponding to this checkpoint, as well as the checkpoint directory that already exists. So there's nothing else that needs to be added on top. One other note is that since we're doing just a data parallel training here, like we're not doing any sharding of model states, we can just report the checkpoint from a single worker. So I'll actually add a little bit more logic, which only reports this checkpoint from the rank 0 worker. This makes it so that we don't have to redundantly upload copies that we don't need, since every single worker has the same state. Okay, so we're just using some other ray-trained utility APIs to get like who is like the rank 0 worker, and every other worker should just report none in this case. Oh shoot. Sorry about that. Okay, the next part is actually implementing restoration logic. So this part is actually pretty simple as well. So I'm just showing like the live coding here. We first get the checkpoint, the latest checkpoint, and this is when we restart our training script. When Ray reschedules this job, we will have this checkpoint be populated, and we will actually just download it using this as directory API. And so now we have it as a local checkpoint directory, and we can just use Accelerate's load state API to just load it back. And we've also saved a little bit of extra state, for example, the training's global step, and we're just loading it also from this directory. So you can pretty much save like in whatever format you want. There's no restriction here. It's just like however you define the checkpointing logic is how you should just load it in the corresponding way. Okay, so now that we have these two added, there's just one more piece that we want to add, which is the experiment tracking tool. So let's actually just use 1DB. So the recommendation here is that we can just use 1DB directly, and we just have the rank 0 worker initialize 1DB with a unique experiment name, and we can also use it to track the checkpoint as an artifact later on in training. So I'll just skip ahead. We'll take a look at the dashboard later in the demo. Yeah, so basically we can start running the experiment now after implementing the 1DB logic. I'll just skip ahead. One other note for the 1DB API key. So because we're going to be, like we don't necessarily know which node the rank 0 worker is going to be scheduled on, we want to make sure that this API key is available on that node. So we're just going to use the Ray runtime env to make sure that that API key is available on every single node, and just pulling from the driver of the head node. Okay, so I'll just quickly go through. Basically, all I'm doing here is just running the script with 4 workers. And I'm waiting until I see that the checkpoint is actually reported to RayTrain. So basically, the checkpoint gets uploaded to S3. There was like a log earlier, so I like kind of skipped it. But now I'm just showing the actual GPU utilization in the Ray dashboard. And then also the logs in 1DB. So we can take a look at the metrics that we reported, as well as the checkpoint artifacts that we've tracked. So we can take a look at the files, as well as some metadata, which also includes like the metric associated with the checkpoint. Okay, and the last thing I wanted to show in this demo is I'm going to launch a script that just kills one of the nodes. So once one of the nodes gets killed, this is just to show like how the fault tolerance works in practice. Once one of the node dies, you'll see this log that Ray tells you that it's missed too many heartbeats, and the training is going to restart. And then the last part of the script is just showing that training is restarting, the dashboard is updated with all the statuses of the node getting terminated and the new node coming up. And then eventually we see that the restoration logic starts coming into play. As we can see, this print statement is starting to restore. And then eventually, after it downloads this checkpoint and loads the state back with Accelerate's API, it will just resume training. And we can see that the total number of training steps has decreased because we've restored from a certain time step. Okay, that's pretty much all there is to the demo. Thank you, and I'll accept a few questions.